Okay, good morning and welcome to this session on compression for scientific data for ECP application. I am Frank Capello from Argonne National Laboratory. Welcome. And as you see, there will be many speakers today to talk about compression and lossy compression for ECP applications. You see a quick example here of what could be done with lossy compression. This is compression of data coming from the LCLS for crystallography. And you have on the left side the reconstruction of an electron densities lysosym from non-compressed data. And on the right side, you have the same reconstruction from compressed data that has been compressed with a compressor design with LCLS in the context of ECP. And that provide a compression ratio of about 200. And what can be seen here is that for this analysis, there is almost no difference between the initial data and what could be done with the compressed data. So this is, in fact, reflecting the topics that we will discuss today. We will discuss about compressors. So what are the technologies that are developed within ECP about lossy compressions? We will also discuss about tools to analyze the error that the lossy compressor provide, and we will also discuss applications of lossy compressors in the context of ECP applications. So let's look at the motivation. If you are attending this session, it's because probably you are already convinced that we need to use lossy data reduction technique or data reduction techniques in order to reduce the data set, the scientific data set. There are different motivations for that. The first one is really to reduce the footprint on the file system, for example, or the footprint in memory, or to accelerate the I/O. So that's one type of motivation for lossy compression. And there is another type of motivation which is associated to that, which is a cost reduction. And that's a motivation, for example, for MGARD to look at data reduction technique for climate data. So there are different types of scientific data reduction methods. You have lossless reduction, lossless compression are part of that. And of course, that would be ideal if we could reach high compression ratio with this type of technique. So lossless gives you the guarantee that you will get the same information after decompression than you get before compression. So that's a perfect use of data reduction. But as you will see, in fact, unfortunately, we cannot really reach high compression ratio with these techniques. And so we need to look at lossy data reduction. And when we do lossy data reduction, as you may imagine, we alter the data. The data is, the information has changed a little bit, noise is added. And so there is here this notion of trade-off between the level of reduction that you can reach with lossy reduction, but also what is the level of error that you have introduced in your data set. And so this is this trade-off, which is very important to look at and to estimate. And this will be, I would say, the core of the discussion for today's presentation. So to give you an idea of how much compression we can get with lossless compressors, so you see here on the left side at least two of the ECP dataset plus some dataset on climate and weather, and you see lossless compression with Z-standard, with BLOSC, with FPZIP, with FPC, with ZFP, but ZFP in lossless mode, and you can see that the lossless compression, is providing compression ratio of 1, sometimes 2, sometimes 3. ZFP has a very good job to reach 3 or more than 3 on lossless compression for exaflop. But this is still not enough for most of the application, and so we need to go and to test lossy data reduction technique. So how this is done? So this is the typical pipeline for a lossy compressor. You have a first stage that does some decorrelation, so pre-processing of the data, and then you have a stage which is doing the approximation. This is where we introduce the error in the lossy compression. And then you have the coding stage. There are different ways of doing the approximation to introduce the error. I will not go into the detail here. Each compressor that will be presented today will discuss this in detail. But what I would like to say for the community is that, in fact, if we look at these three stages of lossy data reduction or lossy compression, in fact, most of the research was done in the past 6 years on the decorrelation aspect. So people have tried transforms. So ZFP, one of the compressors that will be presented today, use transform. SZ, another compressor that will be presented today, use predictor. And then you have MGARD that use the multi-grid technique. Some other compressor use SVD. So there is a very large diversity of methods to do the decorrelation. And this was, as I said, the core of the research in the past 6 years. But now the focus, it seems, is more on the approximation stage where we try to improve, or the different teams try to improve the preservation of features. So what features mean, what preservation the user wants. And so this is probably what will be the core of the research in the next few years. And then there is the coding stage. And here there is almost no research in the teams, in the different teams looking at compressors, because there is already a lot of results, and this is, the theory of this is 70 years old, and so there have been a lot of results. There is no room for big progress here. So you have different use cases for lossy compression of scientific data. The most used or most known one are for visualization, of course, for the reduction of storage footprint, or for the reduction of I/O time. But there are also new use cases that have been identified during the ECP projects, like reducing streaming intensity for the instruments like the LHC, for example, lossy checkpoint restart, recomputation avoiding, running larger simulation by reducing the memory footprint. And there are other use cases beyond ECP, like application for AI, how you can accelerate AI training by using lossy compression. So there's a question in the community, and you can imagine is if you are a developer of an application or a user of an application, you may ask this question to yourself, which is, should I develop my own lossy data reduction technique, my own lossy compressor? And if we look at the diversity of the domain sciences, the diversity of use cases, the diversity of the data sets, in fact, you may end up, if you follow this strategy, you may end up with hundreds or thousands of different compressors. And that may not be a good service for the community because well, the lossy compression technique is still improving. And so it's hard to keep up for people with the development of the new algorithm. And it's also important to provide reliable compressors, reliable tools that are production quality, and that's hard to maintain that many different compressors. And so that's why the tool that will be presented today are generic lossy compressors that have been designed to work with many different data sets and for different use cases. So of course, if you are fully generic, you may not reach the best performance. And so the community has looked at ways to improve that, to go toward the performance of fully specific compression techniques. And we have explored different ways of doing that, using meta compressors, for example, that select the best compression technique according to the characteristic of the data set. People have developed preconditioners in order to prepare the data before using generic lossy compressors. And some compressors now are customizable. So this means that you can customize them in order to improve their performance. High compression ratio really depends on the app. So the expectation that you can have in terms of how much compression you can get on your data set really depends on your application, on your data set, and on the quality of the data that you really want. And high compression ratio really depends also on the difficulty to compress the data set. For some data set, it's easy to get compression ratio of 100, I would say, for visualization, for example. For some other data set, like HAC, for example, it's very hard to get a compression ratio of 5.
Frank, 5-minute warning.
So that's one aspect of it. Lossy compression is good, but then you should look at the expectation you can have depending on the complexity of the data set that you need to compress. But there is this other aspect that we really need to consider, and this will be discussed during the presentations today, the different presentations, is really how do you assess the error that the lossy compressor has added in the data? How do you assess the impact on the analysis of using lossy compressed data instead of using the real data? And so there are different levels of assessment, and the first level is just visualization. And so you start visualizing the data, and you can see immediately there are some big things going wrong. So for example, you can see that on the diagram on the right side. On the top, you see that there is some meshing appearing, so that was not in the initial data. So these type of features that are added by the compressor are maybe not good for you. If they are not good, you can use visualization, maybe is enough to see that. But then when you are happy with visualization, sometimes there's still some level of error that you want to understand, and you can use what's called the level 2, which is a quantitative assessment of the lossy compression error. Here you use tools that perform some statistical analysis to understand the structure of the error. All the aspects of these errors, how your data has been affected. So this gives you more insight about the deviation from the initial data and whether you will be happy with this type of deviation or not. For example, some compressor may add autocorrelation in the data set. This may add some features. They may not be visible on visualization because they could be small. But then with this type of analysis, you can discover that there is some autocorrelation, and you may be happy or not with what you see. And the third level of evaluation is really an important one, is to look at the analysis which is done on the compressed data, so the down the line analysis, and see how it is impacted by lossy compression. And so you compare, in that case, the analysis on the initial data with the analysis on the compressed data and its impact, and you can assess whether or not you are happy with that. We will present tools for the L2 and the L3 analysis. So this is the agenda. At 10:15, in 2 minutes from now, there will be the first talk on compression techniques. So we start with compression techniques. You will see 4 different compression tools. And then after that, we start looking at methods and tools to look at the error that is introduced by the lossy compressor. The afternoon continue with these tools and methods to assess the compression error. And then the end of the afternoon, or I should say the core of the afternoon, will be on applications and how these different ECP applications are using lossy compression techniques. What are their results? Are they happy or not? I suppose they are, otherwise they will not present here. But you will see for different type of application, what's the benefit of using lossy data compression. So just some logistic aspects. Please mute yourself when you are not speaking. Each talk will have about 5 minutes of Q&A. So this is at the discretion of the speaker. This is maybe less than that or more than that. There will be a discussion session at the end of the second half on the afternoon. So it could be 15 minutes if we have time. And if you want to ask questions, please ask question on Zoom or raise your hand, and you will be able to ask the question orally. So I would like to thank, before we start, I'd like to thank all the presenters, of course, and you, the attendants, but also I'd like to thank ECP, who is funding all of the tools that will be presented today, and the effort of developing lossy compression for scientific data. So I think we don't really have time for questions, and this was just an introduction. You will probably have questions for the different speakers. And so we will start now with the first presentation of SZ by Shengbi.
Okay, so can you see my screen?
Yes.
Okay, great. So hello everyone, my name is Sheng. I'm from Argonne National Laboratory, and in this talk, I'm gonna present the update of SZ. Okay. So before introducing more details about SZ, I would like to talk about the use cases. SZ is an error-bound lossy compressor, which can be used in many different use cases across different scientific domains. So in this slide, we demonstrate some examples. For example, SZ could be used in reducing I/O time for HPC simulations. For example, HACK and NWCAM. It can also be used to reduce storage footprint or memory footprint, communication costs, or reducing data stream identity. For details, you can read our paper published in IG HPCA 2017. Okay, so SZ is a kind of framework, and up to now, we have developed many different versions. So this slide demonstrates the whole family tree of the SZ software. Basically, SZ could be split into two categories, production and research. And in the production category, we can also split the software into generic category and the specialized category. Under the generic category, all the compressors listed here are designed for the general purpose usage. So they can be used to compress the different type of the data stored in the regular mesh. And for the specialized category, basically we customize the compressor for different specific applications. For example, we developed the Petri SZ for quantum chemistry applications, and we developed the MDZ for molecular dynamics simulation datasets. Okay, so we also have the research line to explore the different lossy compressors for different applications or different devices. Okay, so we have a very big team, and the team members are listed here. Okay, so in this talk, I will mainly talk about our new version of SZ, SZ3. SZ3 is a composable error-bounded lossy compression framework for scientific data sets. Basically, it is largely different from our previous version SZ2 because we refactor the whole code such that SZ3 is very flexible. So more specifically, the users can customize the compression pipeline by themselves based on SZ framework. In SZ2, since SZ2 is coded in C programming language, all the components and the compression stages are tightly coupled, such that the users cannot flexibly, play with the different compression stages to customize the new compressors. In SZ3, it is very convenient. So here is an example. On the right-hand side figure, you can see that different compressors actually are composed of different compression stages. For example, SZ2 is the right curve here. It composes the Lorentz plus regression at the predictor and the linear scale quantizer and Harman encoder and this standard. Okay, so we decompose the stages for users to be able to customize different compression pipelines very simply. So this slide demonstrates an example, several examples. Okay, in SZ3, for example, if you want to, sorry, if you want to customize the SZ2.1 compression pipeline, what you need to do is just identify the preprocessor and identify the predictor to be Lorentz plus regression, and also determine the quantizer to be linear scaling quantization, and also identify the Harman encoder and this standard at the lossless compressor. And then you can just put them together in a function called SZ compressor, and that's it. Then after that, you can just use the corresponding compression pipeline to perform the compression. Okay, so obviously this is very flexible and very user-friendly. The users can customize the compression pipeline by themselves to adapt to different data sets, right? Okay, so I'm gonna show several successful stories based on the SZ3 framework. Okay, so the first successful story is at the interp compressor. This compressor is published in ICDE 2021, and it can significantly improve the compression quality over the previous version SZ2. Okay, so basically we replaced the previous predictor used by SZ2 by another more effective predictor, which is called dynamic supply inflation. Okay, and you can see that. So I demonstrate some one application as an example here. You can see at the interp has much better rate distortion than all other state-of-the-art compressors. For information, IDE 2.1 was published in IEEE Big Data Conference in 2018, and IDE Hybrid is the work published in IC 19, and the IDE SP plus PO appeared in HBDC 2020, sorry. So obviously at the interp is really outstanding in this data set. And in this visualization, we can also see that SZ3 significantly improved the visual quality than SZ 2.1 compared with the original data set with the compression ratio of 196 on this data set QMC pack. Okay, so another good story is the Petri, which is a customized compressor for 2 electron integrals dataset in games. And this work was published in Clutter 2018, and it received the Best Paper Award. Okay. And we not only integrated the SZ Petri compression pipeline into the SZ3, but we also improved the some stages such that the overall compression ratios can be improved further. Okay, so according to this figure, we can see that for 3 different data sets, the green curve is the SZ3 Petri, and it can significantly improve the PSNR with the same bit rate on this data set. Okay, so the third interesting story is MDZ, a customized compressor for MD simulation datasets. And this is a collaborative work with EXALT project. Specifically, we customized a very effective predictor based on the molecular dynamic dataset patterns, and then implemented this compressor based on the SZ3 framework. And this slide demonstrates some evaluation results. RDF is a very important metric to MD researchers. And we can see that with the MDZ, when the compression ratio is about 10, it can preserve the RDF feature perfectly. But with the same compression ratios, other compressors suffers very significant distortions. Okay, so in addition to SZ3, we also developed an ultra-fast error-bounded compressor, which is called SZX. SZX is very fast, especially because of its super lightweight operation. For example, it just composed of bitwise addition and subtraction operations. So it could be extremely fast, but its compression ratios will be reasonably lower than SZ and ZIP. But it is still about 3 to 124, depending on error bound and data sets, and it is much higher than this standard. Okay. Okay, so This slide demonstrates how fast IZX will be compared with the other two state-of-the-art lossy compressors, IZ and ZIP. So for CPU, we can see that IZX is about 3 to 5 times as fast as IZ and ZIP. And for GPU, on A100 GPU, we can see that IZX, the cool IZX could be about 10 times as fast as cool IZ and cool ZIP. Okay, so as I mentioned previously, SZX is very fast, but it suffers from the lower compare ratios. So it is also important to accelerate the QSZ because QSZ has higher compare ratios. And in the past year, we also significantly improved the QSZ's decompression performance. Specifically, we boosted the half-mind decompression because it is the significant bottleneck in the whole compression pipeline. Okay, and we, according to this figure, we can see that QSZ's decompression performance has been improved twice as before. Okay, so let me conclude my work. This IZ. So basically, IZ3 is a composable error-bounded lossy compression framework, and it can be used to customize different compression pipeline very conveniently. And I demonstrated 3 successful stories: IZ3 patchy, IZ3 interpolation, and MDZ. In fact, we have more successful stories, but because of the time, I cannot show all of them here. And IZX is a super fast error-bounded lossy compressor, and this work has been accepted by HPDC 22 of this year. And the QSZ's decompression performance is also improved significantly because of the accelerated half-line encoding. Thank you.
Okay, thank you, Sheng. We have time for questions. There are 2 minutes. So there is a question from Ng Wang in the chat. Could you elaborate more on customizing the compressor for specific application like MD? Do you take advantage of data correlation in the application?
Sorry, you mean MDZ compressor, right?
Well, yes, in the MDZ compressor. Okay,
so yeah, basically, I think, yes, in fact, we are going to have a talk this afternoon to particularly talk about MDZ. So basically, based on in a nutshell, based on the MD simulation data set, we observed that some data sets have very interesting patterns. For example, repeatable pattern and the multi-level patterns, and we leverage those patterns to improve the prediction accuracy. And for other data set, we observed that the data set had very high, correlations across different adjacent snapshots. So we also leverage the temporal smoothness. The more details will be covered this afternoon.
Okay, thank you. Maybe one time for one more questions. For an HDF5 application, what compression algorithm would you recommend?
HDF5?
Yeah.
So in fact, I think I'm not sure if I can answer that question because HDF5 is the IO library, right? So how to determine the compressors actually depends on the applications or users' requirement. So for example, some users want to get high compression, and some users want to get very high compression speed. Right? So HDF5 is just IO library, but HDF5 can already integrate different compressors using the H5Z filter mechanism.
Okay, so we will need to switch the presentation to Peter Lindström and ZFP, but Sheng, you can still respond to the question in the chat. There are more questions.
Sure, no problem. Thank you.
So Peter.
Okay, can you see this in full screen?
Yes.
Okay, great, thanks. So I'm Peter Lindström from Lawrence Livermore Lab, and I'll be talking about the ZFP compressor. So ZFP is a little bit different from some of the other compressors you'll be hearing about today. So what is ZFP? Well, I like to think of it in terms of three separate components. First and foremost, it was really designed to be a really efficient and compact number format for small blocks of numbers, small multidimensional blocks. And as such, ZFP kind of competes with IEEE floating point, but also more recent number formats such as posits, B-floats, and others. ZFP also provides C++ classes that implement multidimensional arrays. So you actually store compressed arrays in memory that you have random access to. You can either specify an exact memory footprint, or you can impose error tolerances as well. And finally, ZFP also supports sort of the standard use case of compression, where you actually perform a large computation. You want to write your data to disk in compressed form. So it also is a streaming compressor, and sort of competes with SZ and some of the others that we've heard about today. So in terms of how ZFP does this, well, it takes a multidimensional, say a D-dimensional array, and partitions the array into these small blocks of 4 to the D values. So 4 by 4 by 4 values for a 3-dimensional array. And then it encodes each of these blocks entirely independently from the others. Each block gets encoded to a variable length bit string that can then be truncated to fixed length if you'd like to. That sort of simplifies supporting random access to these blocks of compressed numbers. And that's really analogous to what we do with standard floating points. We essentially just round a number to some fixed number of bits. ZFP is really hardware friendly. It's based entirely on integer and bitwise operations. And in fact, we do have an FPGA implementation of it. ZFP also then provides an alternative to standard floating point representations for performing numerical computation. So there are two separate use cases here. Either you provide less storage for the same accuracy, or you provide higher accuracy for the same storage, and we'll see examples of this a little bit later in this talk. And finally, ZFP also provides this really fine-grained knob for selecting the precision or the amount of storage that you need for your arrays. I mentioned that ZFP supports C++ classes for implementing multidimensional arrays that support random access at block granularity. Now, all the details of compression, decompression, and caching and so forth is really hidden under the hood from the user. So the user interacts with these arrays as though they were just standard uncompressed arrays, such as an STL vector and so forth. So what I'm showing here is a short little code snippet on the left here, where we're using standard STL vectors to implement a 2-dimensional array. And on the right, I've highlighted the lines here in orange that are the lines that would have to change. These are just your standard array declarations where we declared an NX by NY 2-dimensional array. The user also specifies, in this case, the number of bits per value of compressed storage in memory. The lines I've highlighted in blue essentially just provide a nicer syntax for indexing into 2-dimensional arrays, but those changes are optional. And then everything else typically works quite well, so you typically don't have to make too many changes to your code. The third use case I mentioned is just standard streaming compression, where ZFP supports both absolute and relative error tolerances. It also has a lossless compression mode if you prefer that. We have a number of different backends implemented, including OpenMP, CUDA, HIP. There's also an experimental SYCL implementation out there on GitHub. We support several different languages, C and C++, but also Python and Fortran. There are also third-party bindings available out there. And ZFP is really starting to see a lot of support in a number of different applications and tools. I've listed a few here. Sort of IO standard, IDOs, HDF5, and so forth. How does ZFP work? So this is just sort of a very high-level description of the compression algorithms. We're starting with a raw floating point array that's been partitioned into these blocks. We perform what's called a block floating point transform, where we align all the floating point values in a block to a single common exponent, the largest exponent within the block. And then the numbers can then just be expressed in terms of integers that are scaled by this common exponent. We perform a decorrelating orthogonal block transform that is sort of similar to the the discrete cosine transform that's used in JPEG image compression. ZFP's transform is more efficient and effective also in intercorrelating data. And then finally, there's an embedded coding step where we encode the resulting set of coefficients 1 bit plane at a time. And out of this comes this compressed stream that can then be truncated, for example, if you want to meet a certain bit budget or error tolerance. All right, so anybody who has played with JPEG image compression is probably familiar with these kinds of block artifacts. And since ZFP is also based on a block decomposition, there's a potential concern for such artifacts. As it turns out, I'm going to start by showing sort of a bad case here where you can actually see these block artifacts. So what I'm showing here is a 2-dimensional field that's also time varying. So we're plotting here for each pixel the average error over time. And as you can see in this sort of inset here, you can actually see this block of 4 by 4 pixels here, and there's sort of this recurring pattern. And there's a good reason for this. We've analyzed all the components that go into the ZFP transform and determined that for one-dimensional data that I'm showing on the bottom here, you essentially end up with 4 different error distributions depending on which position you are within the one-dimensional block. And ideally, you'd want these distributions to be centered on 0. We've recently done some work where we've been really more careful about how we perform rounding within ZFP. We've been able to essentially eliminate this bias and error. So you can see now that all the distributions line up and are centered on 0. So in addition to being bias-free, we can also bound the compression error, either for a single application of ZFP, or also if you're using ZFP, for example, in a PDE solver, where in each iteration, you're going to introduce some compression error that could then potentially magnify and blow up over time. We've been able to provide hard bounds on such errors, also in iterative methods. Excuse me. So what we're showing here is we're solving a particular PDE, the Poisson equation, on a 256 cubic grid. And what you're seeing here is on the right here are actual visualizations of the Laplacian that's been prescribed to be radially symmetric here. So you want these to be perfectly spherical. We're seeing that with half precision, we essentially just get garbage out. Even with single precision, you can see some clear artifacts here in the bounds across the sphere. And using ZFP at only 8 bits per value, you essentially get a perfect result. All right, here's another example where we started off with a double precision velocity field. We compressed and decompressed that field and then apply the divergence operator to it, which gives you the scalar field. You can see at less than 2 bits per value, ZFP essentially has no artifacts. So the question is, why do we get such good results for these differential operators? So what I'm showing in this plot here is the L2 error in the partial derivative of a certain field. And we're going to see how that error changes as you increase the grid resolution from right to left here. Sorry. Excuse me. As is well known, you're going to introduce some truncation error that's associated with the differential operator itself and the fact that you're discretizing the field. There's also some level of roundup error that will kick in eventually. So if you were to plot this for double precision only, you would essentially get this curve that is just essentially the sum of these 2 error components. For ZFP, we have yet another error component that's just associated with truncating the ZFP representation, as I mentioned previously, for example, to a fixed number of bits. So if you were to plot ZFP here, you would have truncation error, eventually compression error would kick in, and because we return double precision values that you can actually perform arithmetic on, you're also going to incur some roundup error associated with the double precision representation. But if you compare this to IEEE single precision, you'll see that ZFP at only 28 bits per value in this case is up to about 9 orders of magnitude more accurate for the same storage. What this shows here is what you can do is also, instead of using a fixed number of bits per ZFP block here in 2 dimensions, you can vary the amount of storage over the domain to essentially allocate more bits to where they're needed. So in blue here, we're only using up to 8 bits per value within a block, and in white, you'll see 64 bits. So by being more clever about this and where you allocate the bits, you can actually do quite a lot better. So what the plot on the right here shows is that if you do this, and you'll obtain the error curve on the bottom here, which is quite a bit better than ZFP in its original fixed rate mode, where you're using a fixed number of bits per block. And of course, we're doing quite a bit better than IEEE single position here. In order for this to work as an in-memory compressor, you have to be really fast. We do have, as I mentioned, a CUDA and HIP implementation. This here shows the throughput and compression for 3 different generations of NVIDIA graphics cards. You can see that we can get up to about 600 gigabytes per second throughput. Of course, this depends on the rate, or the more you compress the data, the faster the compressor is, because you have to output fewer bits at the far right end, and that's really the dominating cost here in CFP. So we've implemented an in-memory ray tracer that uses ZFP. You're seeing the results of this using 3 different array implementations of ZFP. So if we focus on the bottom row here, we're seeing ZFP in its variable rate mode, where we're using only 0.68 bits per value, and we're comparing that to 32-bit IEEE single position on the bottom right here. You can hardly see any official artifacts, but the point I wanted to make here is that just by using less memory traffic, we can actually perform this ray tracing faster in memory using the compressed representation than from an uncompressed representation. And that takes me to my last slide. ZFP is freely available as open source on GitHub. You get the URL there, so I encourage you all to go play with it. Thank you very much.
Thank you, Peter. So we have time for 2 minutes of questions. Any questions? So maybe I will start. Do you see an evolution of ZFP in the next few years, or is it will stay like that?
I don't. We do have some thoughts on improvements in the algorithm itself to make it more hardware friendly, even more hardware friendly than it is. We're also looking into supporting things like what's important, particularly in the climate community, the missing values, for instance. That's something that few compressors actually support. So you might not have temperature data over land, for instance, and you need to be able to handle that. So we do have a number of changes lined up that we believe will be introduced over the coming years. And we're also looking to make another release of ZFP in the coming weeks.
Okay, so you didn't mention, but I think there is an FPGA implementation of ZFP also.
That is true. So we both have, we're working on the decompressor. We already have the compressor. So that's also out there on GitHub. It's called ZHW.
There's a question in the chat. Will ZFP support all modes, fixed accuracy, etc. on GPUs?
Yes, as a matter of fact, that's also something we're working on. We do have certain feature branches out there on GitHub that support variable rate compression. We're currently working on decompression. We have another branch for that, and those will make it into the next release. We're hoping sometime this fall.
Very good, thank you. So this is well the end of this this part of the presentation. Thank you again, Peter. And now we switch to Ben, who will talk about MGARD, which is another compressor developed in ECP.
Okay, hi. Can you hear me?
Yes, and we can see your slides.
Okay, great. Hi, yeah, so my name is Ben Whitney. I'm a postdoc at Oak Ridge. I'm going to be presenting today on MGARD. Most of the talk will actually just be about sort of the algorithm of MGARD and explaining how it works. And then at the end, I'm going to talk a little bit about MGARD's GPU implementation, all of which was done by Jiang Chen. So his name is up here. So here's all the people who are working on MGARD. Again, Jiang is highlighted because I'm going to be presenting a lot of his work today. Okay, so first I want to give a summary of how MGARD works. So MGARD is like ZFP, is a transform-based compressor. It's sort of like wavelets, if you've ever read about those. And the sort of overall outline of how the algorithm works, I think on the left here, I think fits pretty exactly the sort of pattern that Frank was talking about, where you read in some original data, you perform some decorrelation. That's the gold error here. In MGARD, it's achieved by a transform, so a big linear change of basis. And then you take those transform coefficients, that's a lossless compression, lossless step, and no compression has been achieved. So it's just a change of basis. And then you take the coefficients, you quantize them. There you're incurring error, but achieving no compression. So basically you're just changing from like a floating point representation to an int. You're rounding every coefficient. So error but no compression, and then in this final step you encode the quantized coefficient. So there you pass them to a lossless compressor, so you're achieving compression but no error. And to decompress, you just do all the steps in reverse. So today I'm mostly going to be talking about this first step, taking the original data and transforming it into what are called the multi-level coefficients, which I'll be talking about in the next couple slides. So the sort of fundamental object in the definition of these multi-level coefficients, the decorrelation transform used by MGARD, is a grid hierarchy. So that's illustrated on the right here. So your data is given to you as an array of floating point numbers. And in MGARD, we interpret that as the values taken by some function at the nodes of a mesh, a Cartesian mesh. So here, all the circles represent the points in a grid, basically. And so MGARD supports any dimension, and there's some flexibility to the nodes can be evenly spaced, or they can be sort of variable. Because in some applications we work with people, for example, at a boundary, we'll use a finer resolution. So so here all the red, white, and blue circles together would comprise or compose the original grid that the data is given on. And then before MGARD does anything, it defines a hierarchy of nested subgrids. So you start with all the colors, and then red and blue would be the sort of intermediate resolution grid, and then the red nodes alone would be the coarsest grid. Okay, so now I want to talk about how we use that grid hierarchy to define our transform. So the transform is defined level by level. The levels being the levels in the mesh hierarchy. So for each mesh in the hierarchy, we do the following: we take our input data U. We compute QLU, that's the L2 projection of U to that level. So this is the best approximation to U in some least square sense that can be represented on this coarse grid. So here we could imagine our level is currently the red and blue nodes. So we start with the L2 projection onto that level. And then what we do is we compute this pi L minus 1. This is the linear interpolation onto the level below. So we go from the red and blue nodes to just the red nodes. We interpolate, and then we subtract. And this difference is the set of transform coefficients, the multi-level coefficients corresponding to the present level, and then we iterate and go to close levels. Okay, I'll just speed up. So this is just a bit of motivation. I guess I'll mostly skip this, but the reason that we add this subtraction of the linear interpolant is that the projections themselves have some redundancy between them. So subtracting off the interpolant is a way of sort of removing this redundancy. Okay. So now I want to talk a little specifically about how we like sort of the mathematical operations or kernels required to compute these transform coefficients, because these are the sort of efficient implementation of these kernels is like the meat of the work in the GPU implementation. So as I said, it's an iterative procedure. Let me focus your attention on the bottom right here. So it's an iterative procedure. We do the following 3 steps level by level, starting at the finest original level and then progressing down to coarse and coarser levels. So we start each iteration with the L2 projection of our input data U to the present level. So here that would be defined by values on the red. We then temporarily forget about the values on the blue nodes and we take the values on the red nodes, interpolate onto the blue nodes, and then we subtract. So this object here defines our transform coefficients for level L. Then there's a sequence of steps, which I guess I'll skip for time, that lets us go from those transform coefficients down to the L2 projection onto the level below. So that's the object we need for the next iteration of the loop. And then we just progress until we sort of run out of the hierarchy. Okay, so this is all in order n operation. There are sort of efficient ways of achieving each of these interpolation, subtraction, projection steps. Sort of mathematically, what is needed are a bunch of matrix vector products and also solving linear systems. We don't need to form any of these matrices in memory. They're all sort of matrix-free operations. And so as a result, if we can sort of get each of these kernels fast, it should be an order n operation. And so let me just also note briefly that sort of the reason that this can be, that it's a good candidate for GPU implementation is that in multidimensional data, rather than, so multidimensional data, all the operations, say here in 2D, it's a 2D interpolation, of course, a 2D projection, all these things. But because we're working on a Cartesian grid, we sort of are able to define our function spaces in such a way that all the operations we need to do can be done one dimension at a time. So here, if we're trying to do the L2 projection from one level to another in 2D, this can be achieved by doing a sequence of 1D L2 projections. Those are the blue arrows, say in the X direction, followed by a bunch of 1D L2 projections in the Y direction. So those are the red arrows. And so here you can sort of see this is like a natural parallel structure. If we can, it sort of, this is why we thought to implement on GPUs. Okay, all right, I have about 2.5 minutes. So, give me a sec. So now we're talking about Jiang's work. Jiang has been working on implementing this on GPUs. What he's done is he's looked at these different kernels that are required to achieve the transform, the decorrelation step, and sort of analyze each of them separately. Each of them has called for a different optimization approach. So I'll only have time today to talk about this grid processing kernel. Let me just skip straight to that. I think I will also probably skip this. Actually, it's good. I need this. Sorry. Okay, so let's see. As I said, these operations are happen level by level, and so one sort of let me think of how exactly I want to say this. An issue is sort of striding. So imagine here we're in the middle of our decomposition and we're operating on the red and blue nodes. So at this stage, the transform coefficients at the white nodes have already been calculated, and those nodes aren't required in any of the computations. We just skip over them. So in practice, what this means is most of the data that we're loading from memory is not being used at all in these operations, so that if you're doing an operation on the red nodes here, the sort of logically next value might be, here it's only 5 values away in memory, but in practice, you have many more levels in your mesh hierarchy. And so you're loading, say, like hundreds of values only to use one of them. So before any of these stages, we reorder all the values in memory so that the values that are sort of logically close to one another in the mesh hierarchy are physically close to one another. Okay, so that's sort of the first step. The second is well, let's see, this is let me think of how I want to again. Okay, so this is a CUDA optimization used to prevent something called thread divergence. So in the computation of the interpolation, there's 3 stages. So here we have the values on the red nodes. We want to interpolate them to, well, calculate interpolations on the blue nodes, then subtract. So there's, in this kernel, in the transform, there's 3 stages. First, we need to load all the values from memory. Then we need to compute these interpolations. Then we need to subtract. Then we need to store them from memory. So in the, let me check my time again, sorry. Okay, so I suppose this will be the last thing I do. So this is a memory bound operation where the loading and storing is in a sort of naive implementation is the slowest thing. So in the CUDA implementation, we need to organize our threads into warps, and the let's see, way that this is done we do it in such a way to optimize the memory throughput, right? So we'll load row by row because there's very little like floating point operations that need to be done. This is sort of the bottleneck. The problem is then that after we've loaded, say, this middle row, we need to compute 3 different interpolations. So the left and the right, let's see. So at each of these 3 blue nodes, we're interpolating the 4 red nodes. And unfortunately, these interpolations are calculated in different ways, depending on the position of the blue node. So say at the left node here, the value of the interpolant at this node is just the average of the values at the 2 red nodes. And similarly, on the right-hand node, the value of the interpolant at this node is the average of the values on the right-hand 2 nodes. But the value of the interpolant at the central node is the average of all 4 of these. So the issue is that inside the implementation, these warps, or rather the threads in the warp corresponding to this central row are doing different operations. You have branching. And so this causes something called thread divergence. So the threads aren't all doing the same work, which you want them to be doing. So as a result, if you sort of plot what threads in the warp are working at any one time, they need to take turns. You're not actually achieving this the sort of like parallel speed up that you want in this interpolation step. This is occurring again because we organized the threads so that basically the threads corresponding to a single cache line would be working together. And this is good for reading and storing, bad for interpolation. So what Jiang's done is he's after the loading step, he reassigns all the threads to different warps so that all the threads doing one type of interpolation are working together. You don't have any branching. And then after all the interpolation is done, he again reassigns all the threads so that then the sort of organization is optimized for the storing. Yeah. So here, this is the result of the difference you can see here between sort of the top subpanel and the bottom one. Here, there's no branching. All the
then you have 2 minutes.
Okay. Yeah. Okay. So this is basically saying that it works. I can basically skip that. There's also a bunch of auto tuning, which I don't have time to talk about. But higher is faster. This is naive. Blue is naive, sort of original CUDA implementation. Orange is with these sort of thread reassignment type strategies. There's a bunch more I don't have time to go into. Green is those strategies plus auto tuning. Okay, and then the final thing I want to talk about, and we just end on this slide, I think, is something called MGARD X that Jiang has also been working on. So the motivation for this is portability. Well, I suppose there's 2 motivations. First is portability. We're trying to, convince application scientists to use our techniques. And something that they're very worried about is, okay, maybe I'll compress my data using your technique. Am I going to be able to read it in 5 years?
1 minute.
1 minute. Okay. So, so previously our implementation has been written in CUDA tied to NVIDIA GPUs. This is not a good solution. Just at ORNL itself, Summit currently has NVIDIA GPUs, but Frontier, the next machine, is going to have AMD GPUs. So Jiang is sort of writing abstractions for each of the kernels. This is this orange layer, a layer here that then can be sort of instantiated in these different architectures. So for example, in CUDA, in a CPU implementation, or in Cocos. And so in this way, basically, we're going to have just a single code base, and then can be sort of like implemented on these different architectures. And then hopefully both across time will have portability that, what if NVIDIA goes, I don't think NVIDIA will go under, but if it did, we're still good to go. You can use your AMD GPU. And then also at the moment, for example, my laptop doesn't have an NVIDIA GPU, but I could take a data set that was compressed on Summit with the CUDA implementation and decompress it using my CPU.
So we are done on time now.
Great. Okay. All right. Thank you. And please let me know if you have any questions.
Okay, thank you. So unfortunately, there is no time for
online.
So you can ask questions on the chat, and then Ben will respond directly. And now I will share, or Robert, can you share your slide, or I need to do that?
Yeah, you're going to need to do that because Zoom is acting up this morning.
Okay, so I will try to do that.
Okay.
Can you see the slides?
Yep, we can see the slides.
And then
So hello, everyone. My name is Robert Underwood. I'm a postdoc at Argonne National Lab in Franck's group. Today, I'm going to be talking about a couple of different presentations, but the first one today is productive and performant generic lossy compression with Libpressio. This is some work that we presented at the DRBSD workshop at SC last year, and we'll kind of lay the ground for some of the other talks that I'll be giving later today. Next slide.
Can you see the slides or you don't see the slides?
We don't see the slides. We see
Yeah, that's the problem. I will do it again. Can you see the slide now?
We see the first slide. Press the next. There we go. So the first question we have is, how do we use compressors? So what you see on the slide is the representation of how you would use SZ2, ZFP, and I believe a slightly older version of MGARD. I think MGARD's interface is even updated a little bit since this point. But next slide. The immediate thing that you'll notice is that there are tons of little subtle differences between these different interfaces that sometimes change even between versions. Things like, how do you represent unused dimensions? How do you represent the order of dimensions? How do you know whether or not it modifies input is thread safe? How are things configured? So on and so forth. Next slide. And what we find is that we've only talked about 3 compressors, and there are many, many more that are used within the concept of high performance computing nowadays. Next slide. So the problem is that we fundamentally have too many different compression interfaces. What we need instead is a unified, stable interface that applications can adopt and then use as the compression techniques that are underlying them are updated. That way they can take advantage of better compression techniques and achieve performance that they're looking for. This is in some ways the same kind of challenge that led to the passing of the MPI standard close to 3 decades ago now, I think. Next slide. So where do we use compression within the context of ECP and HPC more broadly? We use it in exascale applications. We use it in IO libraries, command line interfaces, to bound user metrics and distributed experiments, in quality analysis tools, in coverage and fuzz testing, and language bindings. And all of this code is code that potentially developers of compression libraries need to implement to provide the robust set of support that users kind of take for granted now with the robust compression ecosystem that we have today. But maintaining all of this is actually quite a bit of effort. So the question we have is, can we kind of solve some of these problems at a higher level of abstraction? That way we can write all of these tools in terms of generic interfaces, and then as new compression techniques and implementations come along, we can solve these same kind of problems once and then reuse the solutions at a higher level. Next slide. So the question we're going to be looking at today is, can we construct an efficient abstraction for lossy compression of scientific data? And spoiler alert, yes. So our contributions in this work is we present Libpressio, a productive and performant generic compression library. We show an extensive comparison of 9 existing interfaces to show the performance impacts of individual design decisions. And then we show that relative to these, that our library has de minimis or practically unobservable overhead. We also additionally show a 50 to 90% reduction in the volume of client code while maintaining at least feature parity with the original compressor specific implementations, often with more features. Next slide. So Libpressio provides common interfaces for many of the things that you're going to do with a compressor, whether it's loading the compressors and initializing them, configuring them, performing compression and decompression, representing data, reporting and handling errors, and computing metrics off of the various compressors. Next slide. So the code that appears on the right-hand side of the screen, sorry for the dimness of the font, but what you can see is that we don't actually have to change very much code in order to switch from using SZ to ZFP. So in this example, we only need to change the code that's selected in the blue box to switch from SZ to ZFP or SZ to MGARD, dramatically improving the productivity that you would have if you're experimenting with a variety of different compressors. Next slide, please. This is a kind of a slightly outdated, but still pretty useful overview of many of the different compressors, metrics, bindings, IO systems, and applications that Libpressio already supports. So this represents you as a user or you as a compression developer, code that you don't have to write. That means that you can focus on things that are more interesting to you, things like achieving scientific results, publishing papers, rather than the minutia of how do we distribute this using MPI or implement parallel compression with OpenMP. Next slide. So if we look at a variety of different compression libraries, each of them have specific aspects that represent some gaps that can potentially have performance impacts. Next slide. So if you ignore the dimension information or you don't represent it correctly, you can reduce your compression ratio from 1.4 to 1.8x worse. If you ignore the data type, you get 1.8x worse. If your compression routine is not embeddable in C or C++ or Fortran style compiled languages, your code can potentially be 1.2 to 2 times slower. Many of the more recent developments in compressors need data types like CUDA stream keys and MPI comms and the equivalent COCOS and AMD equivalents. And by not supporting these accelerator native data types, you can leave a lot of performance potentially on the table. And that's simply because you can't natively serialize these things into strings. And then not allowing features like introspection or third-party plugins can really bloat the amount of code, both in terms of client code, but also code that the compression developers need to write in order to integrate with your systems. Next slide. So at a high level overview, I'm going to talk about some of the key components in Libpressio and what they do. So the first one is the plugin manager, Pressio, which is responsible for initializing and deinitializing the various compressors. How we represent the various options that come from compressors, how we represent the data that comes in and out of Libpressio, the compression plugins themselves, metrics plugins, and IO plugins. Next slide, please. So Pressio, the library interface, is basically what you would use to query what compressors are supported and get their version information in a consistent way. There's no more looking to see, oh, is it in a library function call? Is it defined in a header? You get a consistent way to query information about version. And by being able to query that in a reliable way, you can make code that allows you to dynamically react to changes in the APIs or take advantage of new features as they exist. Next slide. If you're not presenting, could you please mute yourself? Next, we have the Pressio options data structure. Many of these compressors have kind of difficult to modify ways to adopt new compression settings. They may have a struct or certain fields that you would need to modify in order to represent specific configuration settings. Libpressio takes a different approach, and by expressing these things in something that's kind of vaguely similar to a Python dictionary, this key value map that allows you to represent individual settings, you can very easily write code that works for multiple compressors. So I don't show it here, but there also are some higher level key value pairs that multiple compressors will recognize, things like Pressio abs, which represents the absolute air bound, whether that's on SZ or ZFP or MGARD, each of which have their own names for those specific settings in different compressors. Next slide. The Pressio data reference that here is kind of similar to, if you're familiar with more modern C++, something like an MD span or a span type. But it also potentially has this idea of an owning buffer, which is more like a vector. And what you can do is you can represent these contiguous arrays of memory very efficiently. And the way that these data types have been designed is if your compressor supports it, you can actually do what's called zero allocation compression. We'll talk more about that later this afternoon. Next slide, please. The compressor itself has a couple of different interfaces, the most important of which being compress and decompress. There are also batch versions of these interfaces, Pressio compress mini and Pressio decompress mini, that can operate on multiple buffers at the same time, potentially achieving a speed up. We also provide configurable, which is this idea of allowing us to get at compile time configurations that are specific to compressors, as well as the ability to get compressor specific metrics. So for example, if you're using the SZ2 class of compressor, they have a lot of built-in metrics that can be turned on with a compile time configuration to get things like what percentage of blocks used Lorenzo predictor as opposed to the regression predictor. So these can give you a lot of insight into how exactly the compressor is performing, and it gives you a consistent way to get that information from whatever compressor you may happen to be using. Next slide. Another kind of key insight from Libpressio is this idea of meta-compressors. So meta-compressors are not compressors themselves, but they provide kind of common services above the actual compressors. These can be things like scripting interfaces, configuration tools, pre and post runtimes, parallel runtimes. And we'll be talking a little bit about the auto configuration tool opt-z-config a little bit later during this session today. Next slide, please. Pressio metrics allow you to basically provide hooks before and after each function that's provided on the compressor. You can use these to implement generic versions of error reporting metrics that you may care about for your compressors. Next slide, please. And then finally, Libpressio has this notion of an I/O. These are kind of a set of helper methods that will help you read data into Libpressio supported data types. While for things like POSIX, you may not necessarily feel like you need this, but if you're looking at GPU-based compressors, you could potentially take advantage of the CUDA-based implementation. So if you know that you're on a system that's using CUDA, with a single change in configuration, you can load the data directly into the GPU and bypass the CPU storage and do these kinds of optimizations. Next slide, please. So lastly, we tested over 35 different configurations with 30 replicates for performing a variety of different compression tasks. And what we found is that the largest overhead we observed was 2.08% with a median overhead of 0.47%. Using a Wilcoxon sign rank test, which is a non-parametric statistical test, we find that there is insufficient evidence to conclude that these overheads are different from zero, or they meaningfully differ from zero. Now, concluding, therefore, that there is no overhead would be unrealistic, but it does suggest that any overhead that does exist is de minimis, that it doesn't matter in most cases. Next slide. Now, as to compressor productivity, we looked at a variety of different use cases for representing multiple compressors together, and the number of lines of code used to implement this particular interface for all of the compressors that Libpressio supports that were also supported by this tool. And what we find is that we can receive at least a 50% reduction in the complexity of the code. Most of this comes from consistent air handling and consistent configuration of the compressors. Next line, please. Libpressio also has a command line interface to make it easy to experiment with these compressors before you integrate it into your application's code. I don't have a ton of time to talk about this at the moment, but just know that this exists. Next slide, please. And I want to kind of motivate what you can ultimately build with something like this. So Frank showed you one of the images similar to the bottom right. Yeah, thank you, Frank. So one of the things that we can build with something like Libpressio is Roybin SZ3, which allows us to compose not just like aspects of a compressor, but like entire compressors themselves, potentially allowing us to adapt to new hardware designs as they are introduced. So stick around to the afternoon and I will talk more about this particular development. Next slide. We can also do things like handle provenance, regardless of what compressor you may be using. Next slide. So in short, we can handle Libpressio to reduce both the lines of code while having statistically insignificant overhead. So there's a lot of opportunities here. I know I didn't leave a lot of time for questions, but there should be more time for questions after the opt-z-config and Roybin SZ sections later in the day. So if you have any questions, feel free to ask them in the chat now, or I will have time for actual questions aloud later. Thank you.
Okay, thank you, Robert. So unfortunately, we don't have time for direct questions now. People can ask questions on the chat, and we will switch gear now to the second section, in fact, of this data reduction for ECP breakout session. So the next session will really look at different aspects of compression. So the first one is how can we really compare fairly these different compression techniques that have been presented. The second talk will be about how do we know that they are doing a good job. So this is the notion of compressibility. Can we define the compressibility or estimate the compressibility of data sets, scientific data set? And the third aspect is if you have a compressor with multi-parameter, is how you can optimize automatically the configuration of these parameters. And so the session chair for this section, in fact, will be Pascal Grosset. So Pascal, are you ready?
Yeah, I'm ready.
Okay, so I think I will be the first speaker for this one. So I will start sharing my screen. Please keep me on time.
Sure, I'll do that.
Okay, can you see my screen?
Yes.
It's full screen now. Okay. So I will talk now about SDR bench, which is the scientific data reduction benchmark. So this is an initiative that we started at the beginning, in fact, of ECP, and in the context of the CODA co-design project. And so the idea of SDR bench essentially was to look at the possibility to offer to the community of users and developers of lossy compressors or lossy data reduction techniques, a set of reference data sets coming from ECP, most of them, so that people can really experience and compare things, the compression or the compressors in a fair way. So why did we do that? Well, if we look at the situation before SDR bench, essentially the different researchers were developing their own compression methods using well, the data set that they could access, and essentially for simplicity, they got the data set from their colleagues, and then they were developing their lossy compression algorithm based on this data set. And essentially, this was also for a single use case, most of the time for visualization. And so it was very difficult for people who want to develop new compression techniques, or for people who had interest in using lossy compressor, but for different data sets, to understand the potential performance of the lossy compressors for their data set, and for the newcomers, the one who want to develop new lossy compression scheme. It was very hard to be able to compare things together. And so there was a problem of methodology here. And there was also this problem that, as I mentioned at the beginning, most of the compressors that are developed in ECP are generic. Even if you can customize some of them, they are still generic. And so the idea is that you can compress different type of data set, of scientific data set. And so to be able to do that, you need to access a large diversity of scientific data set. Well, the other thing that was not satisfactory, I would say, as a researcher, was that if people are using different data sets to develop their lossy compression techniques, then it's become very difficult to compare the different lossy compressors and very hard to reproduce results if you cannot access the data set. So we were facing a methodological challenge. And that's why what we wanted to do is to create a kind of equivalent of the NAS benchmark or the spec benchmark for the people who know the HPC benchmark or the CPU benchmark. So we wanted to do that, but for compression of scientific data. And so we looked at what was needed in order to develop this set of benchmarks. And so the first thing is that we needed to set up a server where we could put a very large data set and a large collection of data sets. So that was the first thing that we needed to do. Then we needed to offer an easy access and an open access to this large data set, so which means getting all the authorizations by the producer of this data set, so that they could be used by others to test and assess compression metrics or assess compression methods. And then we needed to have data sets from a large diversity of applications. And thanks to ECP, we could collect this data set with that large diversity. But we wanted also to augment this dataset with metadata that describe the structure of the dataset, with properties, so that people knows what's inside this dataset. And an important aspect was that we wanted to give examples of compressor configurations, so that people would know how to use this dataset, how to compress this dataset in the correct way. Because what we have seen in the community often is that people misconfigure the compressor and you don't get the right performance. And then when you compare with your own developed algorithm, you find that your algorithm is better than the state of the art, but that's because you didn't really configure correctly the compressor. And that's your Libpressio that was presented before by Robert was one response to this problem, trying to find a common interface to avoid mistakes. To reinforce that in SDR bench, we also provide the right configuration for the different lossy compressors. And then we give also in SDR bench the metrics that are used, or some common metrics that are used for the assessment of the error, the compression error. But I should say that this is still a work in progress. We need to augment that with more specific metrics for each of the application and the dataset. So what you can get on SDR bench, and we will see that soon, is that you can also find links to all lossy and lossless compressor for scientific data that we know. There might be some missing. If you see some missing, just contact us and then we will add them. So this is also for user of lossy compressor, a kind of reference web page where you can find the latest on lossy compressors and lossless compressors for scientific data. And we also have links to the tools for assessing the compressor errors that we know. And again, if there are new tools, please contact us and we will add these tools into this webpage. So I will try to jump to this webpage now. I suppose that we'll have to stop sharing this page and share something else, which will be the web browser, which is here. Do you see my screen?
Yes.
Yes.
So you should see the SDR bench website with some information at the beginning that says that, in fact, if you want to have more information about each dataset, you need to contact the author of the dataset. And so you can see here the table on SDR bench. There are 14 different datasets. Again, most of them coming from ECP. And I will just spend a few minutes describing what you see here. So on the left side, you have the dataset itself. So here it's a CSM atmosphere, the source person who gave access to this dataset. What is this dataset? This is from climate simulation. What are the dataset provided here? So there are two datasets, one which is a 2D dataset, another one which is a 3D dataset. You see the dimension, the number of fields that you have in this dataset, and then you see the entropy computed here in 8-bit or 32-bit. That gives you an idea of how much lossless compression you can get. It's not correct because lossless compressor also use the correlation that exists in the data, but this gives you an idea of, if you wanted just to code, use a coding technique, how much compression ratio you could get. And this is representing the number of bits that you will need to represent each 8-bit of information, right? So when you have 6.5 or 7.8, you have almost no compression. So here you see the size of the data sets that you can download. So this is for people to know how much space they will need on their laptop or system in order to download the information, the different data sets that are proposed, and then the configuration of the different state-of-the-art compressors. So I think here we need to add MGARD so that people will know how to use MGARD. For these different datasets. For now, we have SZ, ZFP, and we have Libpressio, so the command for Libpressio to compress and decompress this dataset. And you see here the data set in a raw format, and then the metadata. If I click here, you see what's in the metadata, description of the data set. And then I can go to another data set, for example, for this one, to look at the property, and you see some statistics that are done on the data set, so that you have already, before downloading, some information about what you can see in this data set, min max value, average value, entropy, again, of the data set. So as I said, there are 14 different data sets here. This was a significant effort to collect all this information. This is part of the CODAR project to do that, and to spend effort in doing this collection. And this was very useful for people who are developing compressors, because now essentially when you want to publish a paper on lossy compression for scientific data, you can use this set of reference data sets, and people know where they come from. So you have the list of the different lossy compressors and link to them. Several lossy compressors have not been discussed and will not be discussed today, like digit rounding, big grooming, and these are different compressors that you can try with your data if you want. If I am correct, Robert, these compressors are in Libpressio, so people can really test them easily if they want.
Yep, we have everything except for Isabella and DCTZ.
Yeah. And so you also have links to lossless compressors. So as I said, in fact, the idea here is to give you a web page where you have all the information, or most of all the information that you probably need if you want to compress data, your scientific data set. And then we give some generic metrics that are used. But as I said, in fact, one of the issues here is that each application has more strict criteria for the evaluation of the distortion or the deviation that the compressor is doing. And so these are just very generic metrics here, but we need to augment for each data set. There will be another column soon that will give the metrics that the application is really looking for. And here you have the assessment tools, and you see there are not many for this error assessment. Z-checker will be presented today. Foresight will be presented today. There is another one which has been developed by the MGARD people, the climate community, which is called SFS, that you can use to do that. And so I think I will stop sharing this one and go back to the slides. And so, I already talked about the details about the data set, and what's important here is that you can see that there is a large diversity. So your data set coming from molecular dynamics simulation, cosmology, climate, turbulence simulation, and there is also fusion. So they are already covering a large spectrum of different domains, and with different formats. So that you have a data set in 1D, 2D, 3D, 4D. Some compressor can do that. Some others will be specialized in some maybe from 2D and not doing well on 1D, for example. So you have this diversity of data set here, and also something that we are all often asked is the number of fields that you have in this data set. So you see here the number of fields, and for example for CSM you have a very large number of fields to consider when you need to compress this data set.
2 minutes, right?
Yeah, so here, for example, you have zoom on NICs, and again, some statistics about NICs and the type of information that you can find in the characteristic of the file that describes the property of NICs. So what's the benefit of SDR Bench? Well, for lossy compressor developers, this is the richest set of available data set. With clear structure definition, and so it's really very strictly done so that people can avoid making mistakes, because this is really, again, a problem in the community. You need to use these data sets in the correct way, and the compressor in the correct way to be able to compare fairly the different algorithms. And so this is allowing compression algorithm progress, because now we can assess fairly, and peers, external people, can assess fairly the different compressors, and we can compare and we can reproduce the result. And that's new for the community. I think that's a big progress. And so the third element is that if you are a user or you have scientific data set, then putting your data set in SDR bench could help you. And why it could help you is because it becomes a reference data set where people developing lossy compressors will use your data set in order to see how well they are doing, right? And so that's another important aspect for SDR bench. And that's it for today. And thanks. And I don't know if there is time for questions. If not, then I will respond in the chat.
Okay. Thank you, Frank. So there's not a lot of time for questions.
Yeah. Okay.
So people can ask questions in the chat. So I think we can move on to our next speaker, who is Julie Bessac from Argonne National Lab.
Thanks, Pascal. Do you see my screen?
Yes, I can see it.
Okay. Okay. Good. Then I guess I can start. Let me just move the Zoom. It's a bit big. Okay, so good morning, everyone. I'm Julie Bessac. I'm a statistician at Argonne, and I work also with Frank group. And today I want to discuss some topics about compressibility, in particular in the lossy context. And in particular, we have worked on identifying statistical explanatory variable to try to understand, make a first step toward understanding compressibility of scientific data set. And so most of this work was actually published in the DSBRD workshop also last year, and I will also present some updates. Some context here is that, for instance, when you work with a lossless compression, you have the entropy measure that gives you some limit on compressibility of the data associated with the some limit associated with the encoding. However, there are no equivalent for lossy compressors, and especially we have more steps also when we are using lossy compressors. So our start here was to identify some statistics of the data set that could be explaining compressibility. And in particular here, when we mention compressibility, we refer to compression ratios. And once we have identified some of those predictors, we actually also built some statistical model to formalize those relationships between the compression ratios and the statistics of the data in order also to predict compression ratios. And the overarching goal, like I said, was to characterize some theoretical limit of lossy compressibility. And the goal definitely is to be able to understand how far are we from optimality with the existing compressor, how can we improve also existing compressors, and also then for usage that would definitely help also HPC users to have some kind of this measure. So, oops, how do I switch over here? So let me tell you about the procedure that we follow and the quantities that we have been working with. So basically, we've applied a statistical analysis on some data sets and also a compression analysis. So we've run some compressors. So far, we are working with 2D slices of data sets. So most of the data set actually that were presented just before by Frank on SDR bench are 3D data sets. But so we slice them up first for visual ease of the process, and also this enables to create samples that we will use later on to train the statistical model. The compressor we have used are some of the compressor listed that we discussed just before, SZ, ZFP, MGARD, and also we added some compressors that have different compression schemes, and mostly based on truncation and rounding, so the bit grooming and digit rounding. And so the output that we are taking from this compressor in this study are their compression ratios. And we also studied different air bound for those compressors. And some of the statistics of interest that we have extracted from the data set in a compressor-free fashion was a measure of the correlation strengths across grid points. So basically how grid points on an image are related to each other or not. So we have used actually several estimators or proxies to these correlation strengths. So in our initial paper, we used the variogram range as an estimator of the correlation strengths. And more recently, we have moved to the singular value decomposition because it's much faster computationally. Another statistic of interest is the variance of each image. This gives us an idea of the value range of the slice and also still some variability of the image. And finally, we are using also another predictor here, another statistic, which is the quantized entropy. So basically, it's the usual entropy that you may know, but we apply it on quantized data. So we quantize the data, so we sort of mimic a lossy operation, and then we compute the entropy on it so that we have some measure here of lossiness, but also of patterns that is typically nicely captured by the entropy. Okay, so here are some of the data set that we have been working with, some fields of Miranda, some fields of scale let KF, and then we have generated single scale Gaussian processes that we know entirely how to specify their correlation. So we know the correlation that is present in the data. Plus, we also have mixed together those single scale Gaussian samples in order to create more complex samples. Like you can see here, you can definitely see that we've increased the complexity of those data sets. And so let me show you now how the statistics that we have computed on the data sets are related to the compression ratios that we have also extracted on the data sets from a compression step. So here on this column is actually results for SZ, the middle column is results for ZFP, and on the right we have MGARD. On each row, I'm showing different compressors and also combination of, predictors and different combination of the predictors. So on the y-axis, I always show the compression ratios. And then on the x-axis, I show different different predictor. So the first predictor is the correlation range, as I mentioned. So we can see that we see some association between compression ratios and correlation range. We have a different way of association for different compressors. So that's expected because they have different operation steps. One limitation that we had here, though, was this sort of like fork effect. So this is kind of telling us that the correlation range here might not be enough as a predictor on its own to predict compression ratios. So we added the standard deviation, and we can see here as well that we tend to have some vertical alignment here that may also indicate that the standard deviation on its own is not that good of a predictor. I have 5 minutes left. No? Okay. And so what we did, okay, thanks. And so what we decided to do is actually to combine those two, the correlation range and the standard deviation. And that's what we see on this last row. And we see that we have enabled to correct a bit some associations, but still we have not completed a one-to-one association between the predictor and the compression ratio. And this is where why we decided also to use the quantized entropy as an additional predictor. And so we can see here that here I'm showing the same graph as before, except that the color now represents the intensity of the quantized entropy. And here we can see that each of these forks is actually associated with a different intensity of quantized entropy. So we have been able to sort of add also some sort of discrimination of the compression ratios by using all of those statistics together. And so now we have identified those predictors. We want to formalize their link to the compression ratios. And so we did that by using several regression models. So the model that I'll show later on is a spline regression, where basically we are trying to explain the compression ratios as a combination of splines of these predictors that we identified. And a more simple model would have been just a simple linear regression between the compression ratios and those statistics. And so I just want to specify that here, even though our predictors are compressor free, we still need to use the compressor, because we have to extract compression ratios here in order to train those regression models. And I want to say also that we have trained the statistical model for each predictor and then each field of the scientific data set. And so here I'm showing some out of sample prediction results for compressors and for one field of Miranda. And we can see that the match between the observed compression ratio and the predicted compression ratio is pretty good. We are doing a good job at anticipating compression ratios here. And the model is working quite well, actually. And so the set of predictors we have identified and the statistical regression is working quite well from one compressor to another. And actually, even for bit grooming and digit rounding that have very different way of working. Okay, so I just want to show here that sort of some adaptability of these regression models also on other fields of one data set. So basically what I'm showing here is those two regression models were fitted on one field of Miranda. And then we perform then the prediction of the compression ratio for another field of Miranda. So velocity y here and velocity z. And so we can see that the spline regression has been, is really catching the black dots that are the observations, the observed compression ratio. So this model is showing much more flexibility than the log regression. So overall, these models are quite nice and can adapt also to other data sets, even when you fitted them on others. I have 2 minutes. Here, I will not have that much time to go into too much detail, but I just wanted to give just an overview and say that some of the next step that we have to do is try to have a sort of umbrella result that encompasses several compressors. And so that is not an easy step at all, because compressors are really having different operating modes. And so just as a first step, here I have fitted actually this linear regression on all of the compressor of our studies and also for various error bounds. So somehow unifying the model across error bounds does not seem too hard, as we can see some smooth transition from one error bound to another. However, unifying these models across compressors will definitely be more challenging. We do see some compressors having similar trends, and other compressors here have linear trends altogether, but still there is much more work to do in that aspect. Okay, and this is my conclusion slide. So basically we've identified some statistics of the data that are good potential predictors of compression ratios. We have also formalized some prediction model for these compression ratios, but we definitely have more to do. We need to have a unified way across compressors. We also need to jump from 2D data sets to 3D, because that's most of the data sets are 3D right now. Okay, so I stop here. Thanks very much.
Okay. Thank you, Julie. Okay, let me see if you have any questions. So there's a question from Peter Lindstrom to you. So any thoughts on how to account for tensor-based compressors that are invariant to permutations of the data along each axis? Such permutation will destroy autocorrelation smoothness, but will impact compression ratios.
Yeah, it's a good question. We have not thought about those type of permutation yet. Okay, yeah, I need to think of it. I don't have a immediate response. Peter. So, well, I assume.
I think maybe some of the entropy-based measures.
Yeah.
Of course, would be invariant to permutations, but anything based on autocorrelation or such.
Yeah.
Yeah. Okay.
Yeah. Well, so I guess also then the compressor also does not leverage any correlation as well, right? Probably, if it destroys.
That's true.
Yeah. Okay.
Yeah.
Yeah. Okay. So that must be then probably another set of predictors that we could think of to adapt to more general compressors.
Yeah.
Thanks. Yeah.
I don't have any idea myself, but I think that would be interesting.
Okay. Yeah. Thanks.
Okay, we don't have any more questions, so thank you, Julie. So we are now going to move on to our next speaker, Robert, who's going to talk about the OptiZ config.
Yep. So Frank, I think, is going to be sharing my OptiZ config slides. And then can you minimize the PDF viewer so we can see the actual slides themselves, Frank? Frank?
Yes, I have the same issue as before, so I will try to repeat the same thing.
Okay, there we go. Thank you. So now I'm going to be talking about OptiZ config, efficient parallel optimization of lossy compression configuration to preserve user qualities of interest. So this represents some work that was recently published in IEEE Transactions on Parallel and Distributed Systems. And the picture on the right is kind of the motivating question for this talk. So next slide, please. So the question that we have here is, why is configuration search? Why is finding a particular error bound that will maintain a user's particular quantity of interest? Why is that a hard problem? Well, the relationships between these parameters can be often very complex. So if we look at the figure on the right, we see not only noise amongst the individual regions of the error bound corresponding to even a very simple metric such as compression ratio, we also see potentially large changes in this parameter as we go along the domain. So things that like binary search that you might expect would work don't necessarily work because the relationship isn't monotonic. And if we want to use analytic-based methods or specialized compressors, these techniques can either be expensive to develop, requiring a lot of expertise to use correctly. And our question for this work is really, can we get sufficient results with a cheaper development effort? Next slide, please. So when we compare against a variety of methods, I'm only going to be presenting on two of these today, specifically specialized compressors, and then some of the other kind of manual approaches that have needed to be used before. But if we look across even this relatively small subset of metrics that users might care about, there are lots of gaps between the kinds of metrics that users want to bound the errors on and the kinds of bounds that the compressors that have been developed thus far are able to enforce. So what we see is by using an approach like the approach we take in this work, we are able to protect a much wider range of error bounds. Next slide, please. So what exactly is our approach? So specifically, we're going to formulate the problem of configuring a compressor as an optimization problem. So I'm going to take us kind of quickly through this formula here. So we assume that our data is organized into a series of buffers that are part of a larger ensemble of buffers that come from multiple fields in the data set and potentially multiple time steps. We also assume that we have some way to create a decompressed buffer for a particular field and time step. And that particular field is a combination of two factors. It's going to be a combination of what are called the non-fixed compressor settings and the so-called fixed compressor settings. So the non-fixed compressor settings are things often like an error bound that we're going to allow to modify and change over the course of our tuning process. And then we may have other things that we're not allowing to be changed. So for example, you might choose to hold the air-bound compression mode consistent across multiple invocations of your compressor. With these two buffers and potentially some fixed metrics parameters, you're going to compute some user bound, some user quantity of interest. This could be things like the SSIM of 2 images, for example. And you're going to search over a set of feasible compressor settings. And then as formulated in the opc config paper, this can either be a minimization or a maximization. But you can also potentially look at other more exotic things like combinations of piecewise functions that represent bounding multiple metrics at the same time. Or you could potentially transform your problem into a minimization on a quadratic of your thing in order to search for a particular target of an error bound. Next slide, please. So how does all of this fit together? So essentially, the user utilizes the Libpressio compressor interface to interact with a specific meta compressor that we've designed called opt. And opt then speaks through what we call the metrics interface to speak to an application-specific metric, which could be implemented in C++, it could be implemented in R, or it could be implemented using a simple server protocol that we've developed, or an MPI application. The options for how we interact with the specific metrics can be quite robust. And then potentially that can launch an external program for analysis. We've listed a couple of potential applications at the top. And the choice of what configurations to potentially choose is guided by these Pressio search plugins. Of these, we have things like Fraz. For particularly simple problems, you can get away with things like binary search, but in our specific work, we proposed a new method called FMFS, Fixed Metrics Fidelity Search, which allows us to express a greater deal of parallelism than was previously possible. I'm not going to speak about the specific details of how FMFS works in this talk or the details of the metrics interface. If you are interested in these topics, find me during the poster session or ask me during the question and answers period after this talk. Next slide. So now we're going to look specifically at the question of versus specialized compressors. So we have something of a limited set of options that we might wish to preserve for specialized compressors that we can consider here. We can look at things such as the PSNR, which is supported with MGARD. It's possible to support with SZ's PSNR mode. But we can also potentially use opc config to use absolute error bounded compressors to bound similar kinds of concepts. We could also potentially have looked at something like the Sobolev norm. So that there's a lot of options for what we can achieve here. And what we see is that our tuned implementations in opc config generally achieve higher compression ratios than the specialized equivalents. So these specialized equivalents are designed specifically to preserve a particular target. And depending on the specific range that you're looking at, there could be as high as a 320% improvement in compression ratio, while maintaining the specific target, in this case, PSNR values of 60, 70, 80, 90 that we present here, giving us kind of some motivation as to why we would do this. Next slide, please. But looking at compression ratio is not all that you want to consider when you're looking at this. The other question is, how close do you get to the target that you specified? So for here, we show a variety of different applications. And we've drawn in red with these horizontal bars that represent the target PSNR for each of these particular configurations. And when we look at this, we can understand why our compression ratio results generally showed an improvement, which is that opc-config is going to not rely necessarily on mathematical properties to bound a particular air bound, but it's going to instead rely on how close we can actually get the observed PSNR in this particular case to the proposed target. And because we are able to get much closer to the target than what other potential approaches were able to achieve, we can potentially get a substantial improvement in the compression ratio by getting much closer to the target and allowing the compressor to introduce more errors still within the bound of what's acceptable. Next slide, please. Now, this does come at a cost. So in this figure, we represent the compression time in seconds. And what we observe is that the time that we require when we need to do a tuning is substantially higher than using any of the specialized compressors. When we're able to give opc-config a hint from either the same data set or maybe a different field in the same data set, or maybe a different time step in the same data set. So we're able, in many cases, to reuse configurations. And when we're able to reuse a configuration, we can get the overhead down to on the order of 80%. And that's simply because there's a certain amount of overhead associated with making the guess in our current implementation. We could potentially get that lower, but haven't done so yet. So as I said, we see some trade-offs that start to form here by making these decisions about how do we automatically find these things. Next slide, please. So the last kind of set of results that I'll talk about today is what if we have new metrics that we don't and haven't been able to bound before. Things like the p-value of the KS, the Kolonov-Smirnov test. This is a statistical test sometimes used in climate science to detect certain types of errors, or things like the spatial relative error or the Pearson's coefficient. To the best of my knowledge, none of these quantities had previously, obviously PSNR has been bounded before, but the other three quantities had not previously been bounded with a previous compression system. So being able to identify a configuration that meets the user's quality requirements and achieves a maximum compression ratio is something that we previously had to rely on a systematic approach. So what do I mean by a systematic approach? Basically, you take some plausible area where you might find the solution, and you just keep trying things until you find something. And remember, you can't use binary search because the binary search that you're using, the results aren't monotonic. So like, for example, halfway through the blue bar, we see non-monotonicities in compression ratio that would break binary search being able to search over these particular region. There's another one kind of maybe about an inch to the right of the black line. So these non-monotonicities would make things like binary search not necessarily work particularly well. So what are we able to achieve? So what we're with opc-config, we're able to be 27 times faster on 1/4 as much hardware as what a systematic solution would find. And we find when we find that systematic solution, the compression ratio that it identifies is actually worse. So there's a lot of potential opportunity here for using optimization-based approaches for automatically identifying configurations that meet users' quality objectives. Next slide, please. What about things like execution parameters? Many of the concepts that we've talked about today just translate. Compressors are essentially a form of data flow. Here we show optimizing CFP's runtime based off the number of OpenMP threads that will be used for the execution.
So 3 minutes.
Yep, thanks. Now, this is a particular area that's kind of interesting because it kind of points to an area of future work, because a lot of the metrics we've talked about up until this point are relatively deterministic, whereas things like execution time are not. So this is kind of an interesting area that's worth thinking about, but we already have some potentially good results that we can start talking about. Next slide, please. At that point, I will take any questions.
Okay. Thank you, Robert. So we do not have any questions in the chat at this point. So, and it's noon, so I don't know if people want to end early or just hang out for a small discussion for the first part of the session. Frank, any ideas?